In this chapter, we will be looking at polynomial functions. In this lesson, we'll be working with polynomial functions. Workers were improving a section of highway near Rogers Pass, British Columbia. They used dynamite to remove a rock obstruction. When the rock shattered, the height of one piece of rock as it flew through the air could be modeled by the function h of t is equal to negative 16t squared plus 160t, where h of t represents the height of the piece of rock in feet, and t represents the time after the blast in seconds.
All right, well, the first question here is asking us how long the piece of rock was in the air. Okay, now, if it's not clear right off the top of your head here what it is that we're looking for in terms of the graph, it really does help to plug this in and have a look at what this function is. So let's take a quick look here. Y equals, let's enter that in, negative 16x squared plus 160x. I'm going to press graph. Now I've just got the regular zoom settings in there, so let's press graph and see what we get. Okay, well, now, okay, look what I got here. I got this blue line here, and then I got a little bit of that blue line right there. So let's go to our window here. Okay, well, it doesn't make sense to talk about time before 0 here, and I know my x-coordinate here is going to be time, so let's make that 0. And I saw the blue line right at the very end there, so I'm just going to give myself maybe up to 12. It looks like it might be hitting the x-axis at 10, I don't know. The y-min there, again, it doesn't really make sense to talk about it too deep into the ground here, but maybe we'll give it like negative 2. It's this y-max that I don't really know about. I'm not entirely sure how high up this goes, so I'm just going to take a stab at it. Let's put 50 here and see what happens. Okay, so you see it shoot off there, comes back down again. Okay, well, 50 was nowhere near enough. So let's put up here, let's maybe put 500 there and see what happens. Oh, well, 500 was a good guess, and it really was just a guess at my part here, on my part. Now the question was, how long was the piece of rock in the air? Well, it seems to start at the origin here, and when it hits that x-axis right there, that's we're assuming is where it hits the ground. So if I can figure out what the x-axis is, that will likely tell me what the time it is when it hits the ground, and then that will represent the amount of time it has been in the air here. So second calc to get us into the calculation menu, and we're going to be looking for the 0 of that function. Where it hits the x-axis is called a 0. So the calculator is asking me for a left bound on the 0. So the 0 that I'm looking for, the x-intercept is right there. I'm just going to move the cursor so that's to the left of it, press enter. My calculator does a neat little job, draws a line there. I'm going to move that cursor now so it's to the right of it. Now I'm losing it off the screen, but that's okay. When I press enter, it drops another line right there, and it's going to find the x-intercept, or the spot where the y-coordinate is 0, in between those two lines there when I press enter. And the answer is 10. So what that tells me is how long was the piece of rock in the air? 10 seconds. Okay? Now, B. How high was the piece of rock after 2 seconds? Okay, well, that's a y-coordinate that we're looking for. Height in this case is a y-coordinate. We do know the x-coordinate though. So if I go back into my calc menu, the very first option I have here at value, if you press enter there, what it does is the calculator now waits for you to give it an x value, and then it will give you the corresponding y value. So if I just press 2 in here for 2 seconds, drops my cursor right there, and it tells me that the height here is 256. Okay? So how high was the piece of rock after 2 seconds? 256. And what was it again? I'm assuming it was meters. Yeah. Well, probably, it doesn't actually, I don't think it actually says, or feet. 256 feet. There it is. Next, what was the maximum height of the piece of rock here? Okay, well, that's going to be this point right here. So how do I find that? Well, fortunately, the calculator actually has a tool for exactly that purpose, maximum. So now I'm going to move my cursor over, and I'm always using the left and right arrows here, not the up or down here, always left and right here. So I'm just going to move my cursor here. It just needs to be the left of that maximum. Draws that little line there. I move my cursor over to the other side. I go beyond it, press enter, because what I want is I want my maximum here to be clearly in between these two. And then the calculator was going to bounce back and forth until it finds the point with the largest y-coordinate. it's asking me for a guess. Don't worry, just press enter. And then it pops me right up there. And the point that I'm getting here is 5.0. Okay, that's just going to be 5, comma 460. Now remember, the y-coordinate is the height. So the maximum height that it got here was 460 feet. Let's take a look at the next question. If the height of the rock is 100 meters, how many seconds did it first take to reach that height? Okay, now in this particular question, we're given the height. We're given the value of the y-coordinate. Now, calculator doesn't have a really nice way of dealing with that. So what we got to do is press y equals, and this is where we enter the y values. And I'm going to come down here into y2. That's where I'm going to enter that 100. And now when I press graph, I've got the two equations here, the two lines. Here's the path of the rock, and then there's this boundary here, this 100. Now, I'm interested in the amount of time it takes to get to that point right here, the first time it hits that 100-foot height there. So second trace to get into the calc menu, and this time I'm looking for intersect, where those two lines intersect. Now it's asking me, am I on the first curve? And then when I press enter, it's going to jump to the second curve. But what I'm going to do first of all is move the cursor sort of close to that point of intersection. It doesn't have to be bang on top of it, just close to it. Press enter, it immediately jumps to the other curve here, and I just have to press enter to confirm that those are the two lines that I want to find with the point of intersection. Now, is it okay for the calculator to guess that? Yeah, it's okay. It's not going to make a difference. Press enter, and it finds that point of intersection at height 100 feet, and it's going to happen here at 0.669873 seconds here. So let's round that. Actually, that'll round nicely just to the nearest tenth. So at 0.7 seconds. That's what we're looking for.
The volume of water in a cylindrical tank being drained can be modeled by the function v of t is equal to negative 3.8 t plus 225, where v represents the volume in liters and t represents the time in minutes. How long will it take for the tank to empty? Round your answers to the nearest minute.
Okay, so we want to figure out how long it's going to take to empty the tank here. So here's the formula, or the function for volume as a function of time here. Well, let's just take our calculator and go to y equals, and let's just enter that in. So negative 3.8 x, where am I at here? X plus 225. Now, I've already got the calculator set for just regular old Zoom settings, negative 10 to 10, negative 10 to 10. Let's just press enter, see what we get. Calculator's thinking. Oh, that's disappointing. Nothing. Nothing at all. Okay. Tell you what, let's take a quick look at our table of values and see why. Where are these numbers here? So press second, graph. Now, my table of values is set back a little bit here, but let's just go to 0 here. Oh, that's the problem. 225. That's the value of it when x is equal to 0. And when I go up to 10, it's still at 187. So this graph is substantially above my zoom settings here. Now I'm going to press the window here. Once again, I'm going to plug in 0 for time because it doesn't make sense to talk about negative time, negative values of time. And I've just seen here that 10 seconds isn't enough. So let's make that 20 seconds, or we'll see what happens here. The y-coordinate is the volume of the tank. Doesn't make sense to talk about volume less than 0 because that's when the tank is empty. The tank is empty. It doesn't go negative here. And we've already seen that the maximum has to be quite a bit larger than that. And at 0, it was 225. So let's put 225 in there and see what we get. All right, so there's my line here. Whoa. Now, I want to see where it's empty, meaning I want to see where this thing drops all the way down to the 0 line. Now, I'm not there yet, so I've got to get in there, change that window setting. We got to make that X max heck of a lot bigger. Let's say 50. Let's see what happens at 50. Well, that's looking good. Not good enough, though. So let's try 60. Maybe 60 is enough. Oh, there it is. I can see the point of intersection on the screen. So I hope you kind of see what I'm doing with this. I don't know what the window settings are supposed to be. I'm just kind of taking a stab at it, but I'm using some tools there to help me out with this. So I want to find that X intercept. So I press second trace to get into the calc menu, and I'm looking for that 0. Okay. So now I'm going to move the cursor close here. Now, I'm probably going to end up going off the screen here, but that's okay. The calculator will adjust the window settings for me here. I'm going to press enter because I'm to the left of that point of intersection. Now I'm going to let the calculator, the y coordinate go to the right bound, press enter, and it really basically just takes me right against the line of the screen there. Press enter again for the guess. Ooh, and it's close. It's right on the line here. 59.2. Okay. Round to the nearest minute. Okay, so it's going to be 59 minutes. That's how long it takes the tank here to drain.
A 15-gallon tank is being filled with water and has a pump that will cause it to drain when the amount of water inside the tank hits a certain volume. The volume of water in the tank over a 3-hour period can be modeled by the function y is equal to negative 2t squared plus 5t plus 6, where y represents the volume of water in the tank in gallons and t represents the time in hours after noon on a particular day.
Okay, now our first question here says, to determine the volume of water in the tank at noon, the characteristic of the function that should be analyzed is the, okay, what? Well, let's go back and just take a look at the information here. We're given this function here, where y represents the volume of water in the tank in gallons, and t represents the time in hours after noon. So if we want to figure out the volume at noon, we got to think about how that relates to t here. Well, t is the hours after noon, so at noon the number of hours is going to be 0. So the t coordinate is going to be 0, meaning that we're looking for the y-intercept, and that's exactly it right there. We're looking for the y-intercept. Okay, so there we go. I was looking at all the other options there just to make sure that there was no kind of duplication there. That's what we're looking for. Now, the maximum volume of the liquid in the tank to the nearest tenth of a gallon. Okay, to do that, we need to go back to our graph. So y equals negative 2x squared plus 5x plus 6. I've got the calculator back in my regular zoom settings, negative 10, 10, negative 10, 10. Let's graph. And actually that's beautiful here. The next question I'm answering here is only asking me for the maximum volume, so I don't really need to play with the window settings much. I'm just going to press second trace, and I'll use that maximum feature right there because I can see the peak right there. So I'm going to move the cursor close, press enter, overshoot it, press enter so that the maximum is between those two lines, and it's waiting for a guess, but when I press enter, it doesn't really matter what the guess is, okay? We just got to make sure our cursor is close to it. Press enter, and it's going to give me what that vertex is. So at 1.2, we get 9.125. So the maximum volume here is 9.125 gallons. And now it says to the nearest tenth. Okay, so 9.1 gallons. There you go.
A piece of cardboard measuring 30 centimeters by 20 centimeters is used to create an open box by cutting out a square with length x centimeters from each corner, as shown in the diagram below.
Okay, so the first question that we get here for this scenario is to write an expression for the volume of the open box. Okay, now it's important that you recognize what we're doing here. And this, by the way, can be really confusing for people. So I don't want you to worry about this or beat yourself up here if this is not immediately obvious to you, okay? But I want you to see what's going on here. What we're going to do here is we're cutting out these little squares that are x by x, and then what we're going to do is we're going to take this little bit here and fold it up. So meaning that the height of my box is going to be x, okay? I'm going to take this little bit here, fold it up, so that this portion here is now vertical to the table here, okay, or perpendicular to the table. So when you think about the volume of a box, remember that it's going to be length, width, height. Well, right now I can tell you that our height is going to be x. Now let's take a look at the length here. The length of this piece of cardboard, and I believe it was a piece of cardboard, yeah, is 30 centimeters. But the box itself isn't going to be 30 centimeters because I'm going to fold up this portion and I'm going to fold up this portion. Okay, this little tab here is going to go vertical, this little tab here is going to go to vertical. So instead of being 30 centimeters across, I've cut this portion out and this portion out. Well, I've lost X centimeters on this side and I've lost X centimeters on this side. So, well, what am I left with? Well, okay, 30, but minus 2 X's. So 30 minus 2 X's. Now, when we go back to this, I already know one of the questions that's coming up here, and because this is a really standard question. Okay, it's a very, very common question. At some point here, we're going to be asked about the domain of this function here. Now, watch this. If I keep cutting out the same size of square every time from both sides here, the largest I can cut out is 15. Because as soon as I cut out one that's 15, I've basically cut that thing in half. Okay, so it's got to be less than 15. Now, that's not the only restriction here, but I want you to understand where I'm going with that. If I keep cutting these corners out, eventually from both sides at 15, I'm going to cut it in half. Now let's take a look at the width here. The width of the cardboard is 20 centimeters, but again, I'm going to take this tab and I'm going to fold this up. Okay, I'm going to fold this side up, which means I'm going to lose that little bit and I'm going to lose this little bit from the width. So now instead of being 20, it's going to be smaller than 20. I'm going to lose, and because these are squares, I'm going to lose x here and I'm going to lose x here. So the width is actually going to be 20 minus 2x. Okay? And again, let's think about that. How big can these x's then be, okay, before I'm cutting this thing in half horizontally? And the answer is 10. Okay, I keep cutting in these little squares here. So if I cut 1 centimeter and 1 centimeter in, then I'm going to have 18 centimeters left over. 2 in, 2 in, I'm going to have 16 left over. But if I come 10 in and 10 in, there's nothing left over. So basically, the x value here, the size of the square here, can't be larger than 10. When I looked at it lengthwise, it couldn't be larger than 15. And now I've got an even smaller restriction. Now, that pops up right here. What's the domain? Well, the domain is the size of the box, the x that we're cutting out here, the corners. It has to be bigger than 0, or else we're not making a box. If the length of the square is 0, then it's just a piece of paper. Okay? We haven't done anything. But it's got to be less than 10. Because as soon as it hits 10, I'm cutting this thing in half, kind of horizontally. I'm just chopping in half right there. Now, next question says, determine the length of x that would produce a maximum value. Well, okay, now to do that, what I need to do here is I really want to graph this. So I'm going to take the equation that I just built here, and I'm going to plug this into y equals. That's going to be x, bracket, 30 minus 2x, 20 minus 2x. Now, my window settings are right back at standard zoom settings, so let's just see what happens when I press graph. It's thinking. Okay, it quickly draws a blue line there. Ooh, and I can see that it drew a blue line here. It's got to be really, really tall when the lines look as vertical as they do here. So let's take a quick look at this. It really doesn't make sense to talk about this with x values less than 0. So I'm going to put 0 here. And we've already established that the maximum x value that it can be is 10. It really can't be bigger than 10, or else you're cutting this paper in half. So let's just skip over that. When we're talking about the volume, we can't have a box that has a volume that's less than 0. Now, if you're wondering why, then I just encourage you just to take a couple seconds and think about that a little bit. The minimum that I can get here possibly is 0. Now the question is, what's the maximum? And I don't know. It looked pretty steep here, so I'm going to let's put 800 there. Oh, see, even 800 wasn't tall enough for that. Comes down over there. So let's go back into y equals. Let's maybe make this 1200. Let's go up another 400 there. Okay, that was a good value here. So determine the length of x that would produce the maximum volume. Okay, so second traced gets us into the calc menu, and there's our maximum feature. So we'll come down here, choose maximum. We're looking for that point right there. So I'm going to move my cursor to the left of it because I'm being asked for a left bound. Press enter. Move my cursor to the right, move it past the maximum. Press enter so that the maximum is between those two lines there. It's waiting for me to confirm its guess. Just press enter. Thinks a little bit, and it tells you here that the maximum occurs when the x value is 3.9. Okay? So when x is 3.9 centimeters, that's when we're going to get the maximum volume. And then the last question here says, what is the maximum volume? Well, I didn't even look, actually. What was it? It was 1056.3. 1056.3 cubic centimeters. That is our maximum volume.
A company that produces juice wants to change the dimensions of a particular box, which will increase the volume. The juice box is currently 5 centimeters by 4 centimeters by 12 centimeters and contains 240 milliliters of juice. To create the new box, the company will increase each dimension by the same amount. The volume of a box can be calculated using the formula volume is equal to length times width times height. And note that 1 centimeter cubed is the same as 1 milliliter.
So now we're being asked to find the new box must hold a maximum of 1,000 milliliters of juice. Now, that's going to be the same as 1,000 centimeters cubed. We want to determine the largest amount by which each dimension of the juice box can be increased to the nearest tenth of a centimeter. Okay, now remember we're starting at 5 by 4 by 12, and what we're going to do here is we're going to come up with the equation for the volume of our new box. Remember that what we were told is we were increasing each dimension by the same amount. Okay, so I'm going to take each individual dimension here and I'm going to add x to it. So this is the equation for the volume of our new juice box here. Now, what we want to do here is we want to go in and enter this into our calculator here so we can graph this and investigate the graph a little bit here. So bracket 5 plus x, close it, 4 plus x, close it, and then 12 plus x. Okay. Now I've got the calculator back at the standard zoom settings. Let's take a quick look and see what it looks like when we graph it. Well, that's interesting. Now that's interesting, but at the same time, not very useful to me because remember, x is representing the amount that I'm increasing the dimensions by. These are negative, so that's not really all that useful. So I'm going to change the window settings here. I'm going to make the x max a bit bigger. It doesn't make sense to have this as negative. So let's put 0 there as our minimum. And then I don't even know what to really make the maximum here, so I'm just going to guess at, let's make it 20, why not? The volume is going to be, the minimum is going to be 0 here. That doesn't make any sense to go any less than that. Now, in a second here, we're going to check and see what happens to the dimensions to make the maximum volume equal to 1,000. So my maximum here has got to be bigger than 1,000. I'm not sure how much. Let's put 2,000 here and see what we get. Okay, so we just see this curve go up. Doesn't look like it's coming back down again, but that's okay. So now what we're going to do here is we're going to go into y equals. We were interested in what we had to increase this thing by to get a volume of 1,000. Well, volume is a y coordinate, so we're going to go into y equals, and we'll just put 1,000 here and press graph. So here's the relationship between the volume and the size or the amount that we're increasing each dimension by. And here's the 1,000. That's our goal here. So I want to find that point of intersection. So I press second trace to get into the calculation menu. And I'm going to go down to our intersect option. Press enter. Now, am I on the first curve? Well, the truth is I can't even see the cursor. So I believe I got to move it to the left here because it usually tries to bring it to the center here. There it is. Yeah, it was to, sorry. Yeah, I have to bring it to the left because it's going to start to the right here. Press enter. Drops it down to the second curve, press enter. It's asking if it's okay to make this as a guess, and that's going to be fine. And so there we go. To get a volume of 1,000, we have to add 3.5 centimeters. Okay, 3.5 centimeters to each of those dimensions here to get that 1,000 milliliter volume. So determine the largest amount by which each dimension must be increased. Yeah, we're not asking you for the dimensions, just how much to increase it by. That's what we're looking for.